questions before we move on to our next speaker, though? If not, Elijah, thank you very much.
Thank you.
So then our final speaker for this session, we are running a little bit late, but it's going to be David Jenkins from York University, who's going to be telling us about nuclear applications. He's joining us over Zoom. David, it's over to you.
Okay, thank you. First of all, can everybody hear me?
Yes, we do.
Yes, okay, because I noticed there were problems with the sound before. Firstly, I want to kind of apologize for not being there in person. Unfortunately, my mother was taken very ill at the end of last week and went into hospital, but she now seems to be doing rather better. And interestingly, with all this discussion of medical imaging, one of the first things they did was a CT scan that established what was wrong with her. So that shows the value of that kind of medical imaging in helping to treat patients. So I very much enjoyed the talks which we've seen this morning. I think Elijah gave a fantastic talk about the Mandela Lab, and obviously there's a parallel Mandela Lab at University of Zululand. Having this capacity to work on detectors, develop detectors, and use these technology for nuclear physics is really exciting. And it's fantastic that there are now so many people that have got involved in that and got some training to be able to use that sort of equipment. Essentially, what I'm going to give, I'll make this talk a bit briefer in view of your lunch and upcoming load shedding. I just want to give a flavor of some of the applications that we've developed in the past coming out from nuclear physics, and essentially the labs in which these have been developed now have the same technology that you have. We're not sharing the screen, are we? That's what I'm doing. That's completely idiotic. So now you can see it. Okay, great. So this is all coming from the same labs and the same equipment which has been set up at the two universities. So let me first say that I think nuclear physics is a very interesting science because it sits this sort of interface between other areas of science and other areas of real world applications. So as I show on this slide here, the sort of detectors we use in nuclear physics reappear in different guises in particle physics, astronomy, even planetary science, trying to see what's on different planets. But they are very strongly applied in a whole range of real-world sectors. So we've heard a lot today about medical imaging, but there are many others such as nuclear energy, Homeland Security, so looking at whether people are smuggling nuclear materials across borders, nuclear decommissioning, the clearing up of former nuclear sites, borehole logging, where you use radiation detection to understand mineral structure under the ground. So there are several main types of radiation, as we know, and each of those has very different characteristics, from the alpha particle that's famously stopped by a sheet of paper, to beta particles stopped by a thin thickness of metal, gamma rays, which are highly penetrating and need many centimeters of something like lead to stop them, and then fast neutrons that need many centimeters thickness of plastic, for example, to stop them. So the penetrating and the interaction of these particles is quite different. So I'm going to give an example first that involves semiconductor detectors, look at that in terms of alpha particle detection. So the challenge was the following, and this was very much linked to industry that was historically very important in the UK. The nuclear industry and the recycling of nuclear fuel has led to a large range of buildings that have pipes in them that will have had radioactive material flowing through them at various times in their history. In fact, there are tens of thousands of kilometers of such pipes, which are typically 2-inch or 50 millimeter in diameter. And then on the interior of those pipes, there could be isotopes absorbed onto the surface, which are essentially alpha only emitting. So the most common example of that would be plutonium-239. So if you imagine you have such a pipe, and on the interior of the pipe, you have potentially alpha particles being emitted. Alpha particles already lose energy in air. So if you had your detector at the center of the pipe, that would not be terribly efficient. You would be doing much better to have essentially a ring of detectors all the way around, and then you'd be more efficient, you'd be closer to the source. And if you took that a further step, then the most suitable type of detector for this cylindrical geometry would, of course, be a cylindrical detector. And if you imagine such a detector, then it could be interesting, because you could actually have this detector, if it was flexible, be changing its radius. So if you were going down pipes and you found the change of radius of the pipe, maybe this thing could actually wind and conform to the change of shape. So the very good question was, what sort of detector technology could we use to solve this real world challenge in industry? And what's very attractive, and I guess all the nuclear physicists in the audience here and particle physicists will be very familiar with this idea of building barrels of silicon detectors. So these are semiconductor detectors that are generally thin, of the order of a millimeter or less, and we use them for detecting protons, alpha particles, light charged particles in nuclear physics experiments. But of course, the issue here, a bit like what Elijah was showing with his plastic scintillator sticks, is that normally these are made to approach a cylindrical geometry, but they're not truly cylindrical because these individual detector pieces are flattened and planar. So we had the idea, could we actually make a flexible detector that we could actually make it curved? And my colleagues in the photonics area at York showed us that if you took silicon around 50 micron thickness, you can see in this video here that it becomes a very flexible material. You can actually bend the thing into a cylindrical shape of the required radius. Of course, if you bend it too far, as he's going to do in a moment, then it will break. But in general, as long as you bend it no more than a certain amount, it will spring back naturally to the planar shape, because it's a pure crystalline material. So this looked a very interesting material, same as what we use in our nuclear physics experiments. So we essentially took the idea that we could make these flexible silicon detectors. The thickness of them is quite appropriate, because the range of the alpha particles in the silicon is about 20 microns. So this 50 microns looks very suitable. We came up with a concept of how we would make such a detector and pass it through a pipe in order to inspect the inside of the pipe. And then we went off and actually made such silicon detectors in the laboratory. And I won't go into all of the details of this. Needless to say, this work was done in a clean room, starting with high-grade, high-resistance silicon material. Then there's various cleaning and steps and doping of the material to turn it into a diode. And then finally, one illuminizes the surface to stop light coming onto it, and also to make an electrical contact. And if you want to know more about that development, here at the bottom, we provide the reference to the paper which was published. So this is the sort of final product, these curved detectors, and these could be effectively mounted. You see the electrical connections coming off, and these were then mounted, 4 of them around this probe, which could then be pushed down the pipe to inspect the pipe. So we worked with this company, Chromec, a local British company, to develop this prototype. And here we see a test in the lab. We have an alpha source mounted in the middle of this plastic pipe. This detector is pushed down the pipe, and when it's in the vicinity of the alpha source, you can see these pulses coming on the screen. You pull the detector away and they disappear. So it's clearly detecting the alpha particles being emitted from that source. The next thing we did was do a GeoNT4 simulation to understand the sensitivity of such a detector, because we want to know, can it detect the level of activity of alpha particles on the walls of the pipes that you might expect to find in that industrial setting. So this is a visualization of GeoNT4. I won't talk more about GeoNT4 because a lot's been said about that already just by Elijah. You can see the alpha particles coming off. Our detector is the brown region here. And essentially, to measure it at the level that they want to measure a minimum detectable activity of 0.4 becquerels per square centimeter, it would take about 3.5 minutes to scan 1 meter of pipe, and this was indeed suitable for this type of work. So that was useful to industry. So let me just show now a video finally of this being tested with a more realistic pipe and a second generation prototype of the detector. So here it's just being pulled down the pipe on a wire. In principle, it could be self-propelled or something, but this is just to make a test to see whether one can detect alpha particle activity inside the pipe. And I'll pass on from that now in the interest of time. So that was a very quick example to do with semiconductors. I'll try and show a few examples to do with scintillator detectors quickly as well. Elijah's obviously just spoken about scintillator detectors and some of that, so that saves me some time. There are two main types of scintillator detectors. There are inorganic scintillators like crystals. Another example would be the LYSO material used in conventional PET scanners. So we have these sort of materials, some of which are hygroscopic, meaning they react with water in the air, and they need to be canned in order to be used effectively. So there are a range of these scintillators, with some with more light output than others, some with better performances and energy resolutions than others. The other type of scintillator which we find is the organic scintillator. A good example of that would be plastic scintillator, where it scintillates because of the properties of the organic molecules, particularly the rings and chains in these sort of materials, and that also leads to emission of scintillation light. So all these scintillators rely on emitting scintillation light, preferably linearly in response to the amount of energy deposited in that material. Now, the biggest change that there's been with scintillators, and this was again mentioned by Elijah, is the advent of the silicon photomultiplier. And actually, this silicon photomultiplier technology has been driven by our friends in the medical imaging area, because this is now being very much used in PET imaging. And because PET is such a huge international industry and market, there's been a lot of money put into developing and improving the properties of these devices. So these silicon photomultipliers are a real advance over the conventional photomultiplier tube technology. The photomultiplier tube, we convert scintillation light into electrons that are accelerated and amplified through a complicated structure of many diodes within an evacuated tube. And the essential features of such a device is that it requires high voltage to operate, and it's also a fairly bulky and fragile evacuated tube. By contrast, the silicon photomultiplier is a very compact solid state device which operates at low voltages, maybe 30 to 60 volts. it has a very dense array of avalanche photodiodes on it, each one of which can detect a photon falling on it. And as long as there's more of these pixels than there are photons falling on it, then one can get a proportional signal. So it can carry out effectively the same function as the photomultiplier tube. So let me show you just a couple of brief examples where we've used this silicon photomultiplier technology. Again, I want to emphasize all of this development was done with the sort of instrumentation that the Mandela Labs have. So we talked about PET isotopes this morning and PET imaging. I want to talk about how you can develop a miniaturized detector for PET isotope assay. So obviously, PET imaging has been described extensively this morning, so I don't really want to emphasize about that. But what I'm talking about is how does one determine how much of a PET isotope is in your particular sample, which you're manipulating and then ultimately wanting to put into a patient or a small animal or whatever the application may be. Now, conventionally, this sort of thing is done by detecting the annihilation photons. So you pass the PET isotope in solution through maybe something like this here, where you have a large lead-lined pot, and you have a sodium iodide detector and a photomultiplier tube, the rather conventional gamma ray detector, to detect the annihilation photons. And that is a large and bulky system, because the gamma rays are very penetrating. And I was asked by my colleagues at the University of Hull, which is our next nearest university, where they develop PET isotopes and they have a small cyclotron. They were interested whether we could miniaturize this detector technology, because what they were interested in was so-called lab on a chip. So they make these microfluidic chips where they have very tiny channels on a plastic chip, where this PET isotopes would be flowing and being manipulated. And they said, could we make something very small? So what we developed with them, this prototype here, where the idea is rather than detecting the gamma rays, one tries to directly detect the positrons which are being emitted from the PET isotope. And so what we do is that we have this tiny channel, and we have a plastic scintillator, and the plastic scintillator will react to the positrons, and we have a silicon photomultiplier to detect that scintillation light. So therefore, that whole system that was very large can be sort of incorporated into something now of order of millimeters, that, you know, smaller than a postage stamp sort of size. And in principle, this detector, the response is shown here. It has the same sort of response as that much larger, bulkier detector, although there are some issues about sticking within of the material within the channels. So there's some engineering issues to finally improve. But this was also published a few years ago, and we have a patent with our colleagues in Hull on developing that. And I want to show you now one final example. I'm trying to speed up in view of your impending lunch. So this is a handheld gamma ray detector for Homeland Security. So we worked with a company called Chromec about a decade ago to develop a detector for Homeland Security. So what people are worried about is people stealing radioactive sources and using them for inappropriate reasons. And one thing, particularly a concern, is that they might be used in what's called a dirty bomb, where you use a conventional explosive to disperse radioactive material, for example, in the city, and that would cause real panic and so on. So people are wanting to track radioactive sources in the environment in cities to see whether there's anything like that going on. So we worked with them to put together this handheld detector system. So it was based on the silicon photomultiplier technology coupled to an inorganic scintillator, in this case cesium iodide, to build this initial prototype of a handheld detector. And then this company Chromec repurposed and repackaged that basic detector technology into this system here that's called the D3S. That's roughly a smartphone or pocket calculator sized device that has the same detector within it, now connected to a mobile phone, and through that mobile phone it can be networked to many more detectors. And this has been a very significant advance. If you think about this compared to the old style technology, everything has been compactified down, but it has enormous advantages for this kind of border security that they're interested in, because you can have, the police or other first responders and security people at ports and airports and so on wearing these devices. The people who carry them don't need to know how they operate or do anything with them. They just need to wear them, and it will send back data. It will send back data on how much gamma ray signal is being measured at a given time. It's also a spectroscopic detector, meaning that it identifies the gamma ray peaks, and from that it can identify what isotope is being measured. So that provides more information as well. And by networking many such detectors, for example, in a city, you could triangulate where is this radioactive source, and you can achieve a high measure of security. And then latterly, more recently, Chromec have released a new version of this system where they've used a more advanced scintillator, CLLBC, which has a higher energy resolution for gamma rays. So it has an improved gamma ray sensitivity, but also this crystal is sensitive to thermal neutrons. And that means that this detector can also detect neutrons in the environment. And we don't expect to see neutrons in the environment unless they're from special nuclear materials that we would not expect to find in the environment. So this is a very high sensitivity system. Okay, so that brings me to the end of what I wanted to say. In a piece of, I guess, shameless advertising, I'd like to conclude by showing you that these examples that I've given are found in this book, Radiation Detection for Nuclear Physics, Methods in Industrial Applications, which I published a couple of years ago. Actually, the COVID pandemic and forcing us all to be in our houses gave me time to actually finish this off. So I tried to not only describe these basic detector technologies and how they're relevant, but I've tried to give those sort of topical examples that I give here, with the idea that the student and the reader can get some idea how you can take the technology out of the lab and into some more suitable real-world applications. So I think I'll finish there, and thank you very much again. If there are any brief questions, or maybe the lunch is looming. Thank you very much.
Thanks a lot, David. That was very interesting, and I think it's always great to see some industrial applications of the things that happen in the lab. Are there any questions for David before I know you all want lunch, but now's your chance.
Let me encourage the students to give talks by asking a student to give to actually ask a question. Vivan, your turn.
I actually want to ask about your silicon detector.
Yeah.
How long has that device been around? Because it would be interesting in later on, you will be able to, that device can be reproduced for other nuclear sites that wish to study radiation in particles.
Yes, so we're trying to develop it further now with a British company. So you're right that there's probably other interesting applications in the nuclear decommissioning, because you've got a detector you can sort of get into awkward corners and so on if you're able to change the shape of it. I think the other area which is interesting, which we haven't explored, is how it might be used in nuclear physics itself, for experimental nuclear physics, because having a true cylindrical detector could be really very useful, and it has a much nicer geometry than the sort of detectors that people use. So those are two things to explore, I think.
Well, I think if there's any more questions, anyone wants to ask a question, Elijah? Here, there's a question here at the back. Temitope from Northwest University.
Oh, the camera's really good.
Oh, thank you so much. I just want to ask a question. Does the issue of this true silicon detector have application also in agriculture? I'm just beginning to think along that area because I'm seeing the possibility how nuclear science actually improved agriculture, a production of rice production in Bangladesh to a total of about 6 times, if I should be right. So I'm beginning to see, is there an application of this also in agriculture? Thank you.
I think that's a very interesting area to explore. I know various ways people are exploring radiation detection in agriculture. I think one of them is to look at neutrons scattered from the soil to understand about the water that's in there. I think there's probably several areas that one could look at. It probably needs some more thinking about, a more discussion, but I think that's a very interesting area to think about. Yeah.
Thank you. I just wanted to make an announcement here. Today, we have the privilege to have with us our Dean of National Sciences, Professor Fielding, who is a world expert on COVID-19. And thank you so much for coming, Prof. You're very much welcome. You want to say something?
Thank you. Professor Okay, once again, I would have loved to be here for the entire duration of the program. But you know, so many departments in this faculty, but I needed to be here to just share the excitement with the students. To the speakers, I've looked at the presentations. If I had similar presentations when I was a student, I probably would have ended up in physics. To see the applications that can come from physics, we hear about agriculture, we heard about policing. And I'm thinking about, where is it in Iran, where the container of nuclear waste was just disappeared. And I think they found it now. But imagine the application that we as Africans can look at and the answers that we can find in physics. So you will always have the faculty support for the taste of nuclear physics. I look at the faces in this room and I think there's excitement. So well done from our side, and I will have to rush off, but please enjoy the rest of the week and the rest of the program. Thank you.
Thank you so much, Prof. Fielding. So just before we go for lunch, obviously, I want to thank David Jenkins, who has been the PI for the Mandela Project for these last years, who has taken our students, who have nurtured them from more than 20 students, as Elijah mentioned, went to the exchange program with the University of York, where they have intense training. It wasn't for fun. It was tough work. And thanks to that training, we have students coming. They can build new detectors that may change, may improve how, you know, your devices that you use in the hospital. They are very expensive, but this provides a cheaper technology with similar or even better features in terms of cancer resolution, image resolution. So this is one of the things that we are trying to develop here at Mandela, together with our people, our friends at York. Personally, thank you so much, David Jenkins, for being here again and being part of this big adventure. Let's give us a round of applause. Thank you. So that's it.